Yeah, exactly. Well, maybe I'll email you and ask you in the future if you want one.
I'll take a shirt.
There you go. Hey everyone, welcome. Here is a practice problem. I wanted to make sure that you felt super ready to answer all of those exercise 3 problems, so discuss this. Go ahead and take like 4 minutes to discuss this. The Slido is active. If you have any questions, put them in the Slido. Our wonderful TAs are here to help. And then we'll chat about it. All right, if you haven't had a chance, oh wait, I don't think I made an actual question live on Slido. Can you ask questions on Slido right now, even though there's not a question active? I just realized that. No. Okay, hang on. We're gonna, oh, you know what, we'll talk about this and then I'll fix the Slido thing. Okay, cool. Apparently I just realized I totally forgot to add an actual question to the Slido, but that's fine. So hopefully this looks very familiar. I know that we didn't get to left-leaning red-black trees and tries until Friday of last lecture. I do think you have everything you need to do the exercise, but I figured let's go into more excruciatingly explicit and very similar to your exercise detail, because why not, okay? So we've got a left-leaning red-black tree here on the left-hand side. And remember, the invariants we are trying to maintain are 1, that it maintains the binary search property, and that 2, its balance requirement is that there is the same number of black links from any given node down to the null leaves. That's the second one. The third one is that all red links, which are like those ways to connect nodes without extending the height, that's our like secret little way to make the balancing thing a bit easier on us. All red links must point to the left. It is a left-leaning red-black tree. So right off the bat, do these two trees, are they currently valid red-black trees? Yes. Hopefully you can see they satisfy those three properties. They are BSTs. They have the same number of levels of black connections from any given node down to null, and all red links are pointing to the left. So they follow a similar pattern of AVLs where we are going to insert first to maintain the binary search property. Whenever we insert, we always insert with a red link, and then we may do some amount of rotations or recoloring to establish a valid left-leaning red-black tree according to our three invariants again. So, can anyone tell me, when I first insert 22 into this tree before I do any of the fixing, which node is going to be 22's parent? Anyone? 14? Yes, 14. It's always going to be a leaf node. So we start at 52, we're less than 52. We're less than 35. We're less than 14. Do we go to the left or the right of 14? I agree. It goes to the right because we're maintaining the binary search property. But now, is this a valid left-leaning red-black tree? Which invariant does this currently break? Anyone? It maintains binary search. We did that because that was how we placed it. Is it still balanced according to our definition? Yeah, it is still balanced. So this is technically like a correct red-black tree, but yes. There is a right directional red link, and we cannot have those. So can anyone tell me what is going to have to happen in order for me to fix this left-leaning red-black tree? Do we know the action that's going to occur? Yes. Yes, we are going to rotate. Technically, we call this a left rotation. We are going to take the 14, we're going to rotate it left, making 22 now the parent of 14, so that red link can stay. But now the red link points to the left. We've maintained balance. We've maintained binary search. Does anyone have any questions on that piece? Yes? It's considered balanced because we calculate the balance in terms of height of black connections. We ignore the red. So from 52 all the way down to the null leaves, there is only one black link down any singular path. One of the paths has two red links, but we don't count them. They don't count towards this imbalance. But the black links represent a balance the same length from the 52 all the way down. Yes? Question? Sorry? Yeah, sorry, there's nothing up on the poll. I will fix that after, because I'm going to hit exit, and then you'll see the answers to this, and then I'll go fix the Slido. So let's do one more. Okay, so now on the right-hand side, we've got a left-leaning red-black tree, and we want to insert 67. Do you have a question? Yeah, please. Correct. So it is a different definition of balance. So you're right. The AVL definition of balance is that any given node's left and right child can only have a difference in height of at most 1. This definition is any node's left or right subtree must have the same length path of black connections. So 52 down to, like, 52's left subtree has one level of black connections. Its right subtree has one level of black connections. It happens to have two red in there, but we don't count them. That's the little thing that makes the left-leaning red-black tree easier to implement. It's a softer definition of balance. Good clarifying question. Okay, so if we're looking at this one on the right-hand side, I want to insert 67 into this tree. I'm going to insert to maintain binary search property. Who is going to become the parent of 67 after I insert? Yeah, please, help us out. Yeah, you're the only one that raised your hand, so congrats. Yeah, what's up? 77, absolutely. It's greater than 61, it's less than 84, it's greater than 77, so we're going to put it here. Is this a valid left-leaning red-black tree? No, I agree. Which property does this invalidate? Yeah? Aha, yes. See, I listed 3, but I did leave something off because there's actually all of these sort of complicated rules around the red links. One of the things I'm sorry I forgot to mention is you can't have 2 sequential red links. If you have a red link, its parent or child cannot also be red. Now we've broken that, we've got this angry line. So does anybody happen to know what I am going to need to do in order to fix this? Any ideas how to fix this? Yeah, sure. Rotate right. Aha, yes we do, because hopefully this kind of looks like that AVL line case to us now, and we are hopefully feeling pretty good that a rotate right will rebalance that. So if I rotate right, now what I have is I keep those same 2 red links, but they go from being parent and child to being siblings, and that's okay. And if you think about it, yeah, insert weird conversations about incest. But like, if you think about it, this makes sense in terms that like, we're thinking about this in terms of levels, right? Levels indicate our height. We can't sneak in 2 red links to really extend that height, but we can have as many red links across that same level without changing the height too much and messing up our balance. So now we have valid red-black trees. They maintain all of our properties. No 2 sequential red links. All red links. Ooh, but we've got one problem here. What's another problem? Yeah, thank you. Aha, we now have a red right link. Great. So that actually will trigger more things. What needs to happen is we need to color it black and do some rotations. But the first thing that will happen is a right rotation. I just wanted to show you that. So this is not totally finished yet, but that'll be the first step in fixing this. Hopefully this helps you answer your questions for exercise 3. Yes? So what we're going to end up having to do is we're going to have to like rotate that probably back around and recolor another link. I'll add the final version of this after the lecture, but thank you. Sorry, I didn't put the final version of it. Yeah. Yeah, so there's always a step where we go through and we recolor first, and we will attempt to recolor first because that is an easier code to do. So we sort of like, based on our case, we had to do the rotation, and then we'll do a recolor, and then we'll see if we need to do more rotations. Cool. Yes?
Would this be considered adjacent or this considered adjacent?
So right now, the red links there are adjacent. Those are like siblings. They're on the same level. If this was a red-black tree, meaning we colored the nodes instead of the left-leaning red-black tree where we color the edges, that would be okay in a red-black tree, but in this left-leaning specialized thing, we'd have to do a few more to fix it. So, yeah. Okay. Cool. Okay, hang on. Now I'm going to see if I can do a thing so you can ask questions in the Slido. We're just going to do this. Can I just enable Q&A? Hang on, let's see. It is enabled? You can type in Q&A right now? Oh, okay, cool. I thought I had to have a question active to enable Q&A. Thank you all. This is my first time with it. Okay, great. Oh, look, things are happening. Perfect. Okay. Okay, let's go to announcements. So, congratulations. It is officially week 5. I assume all of you are drowning in midterms right now. I'm sorry. I know we've got one this week too. So your exercise 1 grades got released this weekend. Please note that we only leave the regrade requests open for 1 week from once they open. So regrade requests opened on Sunday. They will close, I believe, next on the 30th. Is that Saturday? What? Huh? Oh. I was like, is something incorrect? It's very possible. Pardon me. So do check your exercise 1 grades. Make sure you get those regrade requests in if you have any questions for your grader. Exercise 3 is due this evening. Exercise 4 will release this evening. I will tell you that exercise 4 is only material for today's lecture and Wednesday's lecture, and it's all auto-graded questions because you have extra work since you're prepping for your midterm, and we have extra work because we got to grade your midterm, so like let's all take a little bit of a break. So it's a shorter exercise this week, just so you're aware. So this is exercises only on Heaps, which are the things we're going to talk about today and on Wednesday. Project 2 is due Wednesday. We are officially in the heat of what I call office hours bonanza. So start early, look at Ed, ask each other questions. We're going to do our best to help you, but do plan ahead to know that office hours will likely be busier than you may be accustomed to. Please start on that iterator. And then we will have a new assignment that will release on Wednesday. It is about Heaps. That's what we're talking about today. Great. And then we will have our exam 1 in person in this room on Friday. I know I've been saying it every day, but I seem to catch a few of you every single time I say it. If for some reason you have a conflict with Friday, there is some reason that you cannot be physically here on Friday, please email the instructor's alias ASAP so we can figure that out. I can do infinite amounts of things for you before the exam, but we're going to have some really uncomfortable conversations if I get an email from you after the exam. Fair? Do us both the favor. Email us now, not later. Does anyone have any course administrative questions? Cool. Okay. All right. So we're starting our new unit. Let's talk about this thing called Heaps. But in order to talk about the thing called Heaps, Heaps being the data structure, we're going to start with the ADT. So we've met queues. Queues are an ADT. You could implement them with an array. You could implement them with a linked list. If you really wanted, you could implement them with a tree, but it would be weird. Priority queues are a more specialized version of the Queue ADT and themselves a separate ADT. They are a very commonly used one, and they are implemented within Java. In fact, you may have already used it if you did the Huffman node program for 143 or 123. It's like the one assignment we kept. And guess what? You may have used one in the intro courses, but your next assignment is going to be to implement one using Heaps. Great. So I think I had a head TA give this the first time once, like many years ago, and they came up with this example, which I now realize is a little dated, but I think it's charming. So imagine you are managing a queue of food orders at a restaurant, which normally takes food orders in a first-come, first-served basis, because we are all equal, are we not? Nothing makes me angrier than to see that table at the restaurant get their food before me when they ordered after me. What is happening there? I'm always upset. But suddenly, Anna Marie walks in, and you know, maybe you a hustler, and you've decided you want to serve her either as fast as possible to gain political influence, or maybe as fast as possible because she makes everybody uncomfortable and you want to shoo her out of the restaurant. I don't know which end you sit on. Whatever. Do you? Or maybe the wonderful staff of 373, those famous celebrities are coming in, and we know celebrities should always get seated first, right? How are you going to manage this queue where you can have items of different priority enter the queue and thus cut the line based on their priority? That's what we're trying to work on today. So, meet the minimum priority Queue ADT. It is a set of values that all implement the comparable interface. That is the requirement. And they are ordered based on, quote, priority. And priority is based on the results of the compare to method. So in a minimum priority queue, if they were all int values, they would be ordered in ascending order, with the smallest value would be at the front of the queue. They have the same type of queue functionality. You've got to be able to add something to queue. You have to be able to remove min, and you have to be able to peek min. Great. Perfect for our situation. They are also designed, printer queues typically have a priority queue where they will let you supersede the priority of other things. It also sometimes can be clever about deciding how to time manage better. It'll sometimes let smaller entries get priority over larger print jobs. If you've ever been that person trying to print the one page while that other person is obviously printing an entire textbook on the free printers in 002, because I know that that goes, they would get to skip the line kind of thing. It's in Huffman coding. And when we get to our sorting unit, I am very excited to show you the sorting algorithm that we can do with these things, because it's actually, in my opinion, the most useful sorting algorithm. Justice for heap sort. Why doesn't heap sort get talked about more often? So the other thing to be aware of is that when we talk about priority queues, there are actually two mirror images of the priority queue option. There is a minimum priority queue, where the smallest value comes out first, and there's also a maximum priority queue, where the largest thing comes out first. You can imagine that the code to program these two different things is almost identical, except for the directionality of a singular, like, alligator mouth, which is the American high school terminology for the comparator operator. I don't know why that's stuck in my head forever. So these are essentially the same. You can always do min or max. Just for simplicity's sake, we are pretty exclusively going to be talking about minimum heaps in this class, but all of the things we talk about, you can just invert and have a max heap as well. Okay, so let's wonder. I'm talking about an ADT, right? And like I've always said, any ADT could be implemented by any data structure. We already got some good data structures, so can we make this happen with the existing data structures that we know of? Like, can we implement this idea where whenever we remove min or peek min, how we accomplish that in either an unsorted array, a sorted linked list, why not, just to make it a little more complicated, or an AVL tree? Think about what it would take to implement this functionality with these data structures. Go ahead and chat amongst yourselves for like 2 minutes, 3 minutes. What's the runtime you would think if you were to use these data structures to implement this minimum priority queue? Go ahead, chat about it. How would you do this? Okay, let's maybe chat about this a little bit. So I have an unsorted array. Can anyone tell me, like maybe in a high-level terms, like how would you implement this minimum priority queue using an unsorted array? Like how would you navigate adding and then finding the min and stuff like that? Anyone have any good approaches that they discussed with their group that they want to share? Yeah, sure.
Basically, you would iterate over the entire array and look for the global minimum of the array.
Yes, that's
Or insert it at that.
exactly. Yes. So with an unsorted array, you're pretty limited. So you could maybe say, like, I'm just going to add it always at the back. But then anytime you call peak min or remove min, you got to start and do that linear search thing, and you got to find the minimum value. But you also, that means you have to compare all the values within there, which is a pain in the booty. Yes?
Why are we using an unsorted array just out of curiosity?
Oh, it's just me being annoying and trying to force you to think about how you're going to implement this functionality, and then I'm going to be like, ooh, wouldn't it be nice if you had a, and then I'm going to show you the heap. So me just being annoying. Asking you to think about the difference between ADTs and data structures. Because I believe where your question is very correctly coming from is, why would we ever do this? And my answer to you is, you probably wouldn't. I'm going to teach you the thing you would do instead, which will be so much more motivated, theoretically. Okay, what about a sorted linked lists? How would you accomplish that? Anybody want to give me a high level of how you would implement a minimum priority queue with a sorted linked list? Anyone? Bravery. Yeah.
You can keep your minimum at the front,
Mm-hmm.
and so then every time you add, you should add to the front, and then you can take off the front to remove the min.
Yes, so we've sort of decided the minimum value, maybe it deserves to live always at your front node. So anytime you add something in, well then you kind of want to go through and maybe add it in sorted order. So the adds are where you would maybe break the sorted order and you sort of add in that sort of directionality to maintain that. Cool, but then you've got to sort and like figure out those things, search to where you belong, you put something in. Great, okay, what about an AVL tree? This one has a bit of a natural sorting to it already. So how would we implement a minimum priority queue using an AVL tree? Anyone else? Yeah, sure.
Because AVLs are already naturally sorted, like you said, you can just add to the AVL tree, and then whenever we're removing, just go to the farthest left range, essentially. That would be the smallest value.
Exactly. So the thing that's really nice about AVL trees is they already have that binary search property, so we know that the smallest value in any given AVL tree will always be all the way to the left. That is a classic interview question. They love that. I don't know why. But let's actually look at the runtimes of these. So that's how we get these sorts of runtimes where, you know, the unsorted array, we have to use linear time to find that thing, find the smallest thing in the list. With the linked list, to add, we have to find where the new thing belongs, but that gives us a really quick remove. And for the AVL tree, we still get the log because we always got to go furthest to the left. Are we okay with those runtimes? Any questions about that? So why would we ever do this? Wouldn't it be nice if instead we kind of had this concept where, well, like the AVL tree, that seemed like the best one overall, right? Like that one was really promising. Except what if instead of having to go all the way to the left, we just sort of added an extra bit of information that maintained where the minimum value is. That is a way to do this. Cool. So let's talk about a new data structure that is kind of designed for this specific thing, but you can use it for other reasons. So heaps, the idea. In a binary search tree, and in an AVL, and in a red-black tree, we really organized the data to find anything quickly. It was all about maintaining that sorted order. That was the important piece, right? Now, we don't necessarily care about perfect sorted order. We just care about what is the singular smallest item. For the rest of the item, I don't really care as much about the order that they're kept in as long as I can quickly get to the smallest item. So, meet the heap invariant. It is a requirement that we put on trees. In this case, we are going to be talking about binary heaps, but you can have trinary heaps and n-nary heaps and all that sort of stuff. So the heap invariant requires that every node is less than or equal to both of its children. It's kind of like the BST property, where instead of talking about left and right children, it's about parent and children. So I will also tell you in this heap invariant, the natural next question is, I don't care if the left or right are smaller or larger than each other. I just care that the parent is always smaller than the two children. The two children might be the same value, they might be different values, and I don't care if the larger child is on the left or the smaller child's on the left. It's just about levels. Smallest node, then, is stored at overall root. Very similar to our linked list, sorted linked list situation, where we got really constant lookup time because it was always sitting at front. Now we've got a tree situation where the smallest value is always going to be at overall root. Super easy to peek. Yeah, great. Thanks. Do we need more invariants? So with that singular invariant, remember when we had that singular invariant for binary search trees? It did nothing to prevent the degenerate tree. And the degenerate tree is that dangerous linear runtime. So it would not help us guarantee good runtime unless we added some type of structural invariant to this. Now, the structural invariants were ones that we had to get really specific. We had to have all those rules for red-black trees because we were both maintaining the binary search property and a balance property. And the binary search property is stricter than the heap property. But since the heap property is a little looser, we can end up with kind of some looser structural invariants as well to maintain a more balanced tree. So here is the heap structure invariant. A heap must always be a, quote, complete tree. A complete tree is one in which every row except potentially the last is totally full, meaning the space for all children are used up. The only gap that is allowed to exist in the heap is on the very last row to the extreme right. So the way that a heap fills up is top down, left to right, very like the way you would maybe read English language on a page. So we fill it in left child first, then right child. We must fill in all children across a row before we can create a new row. We leave no gaps. So this tree on the left here is considered complete. We have filled up the 4's left and right children. And the only gap is 5's right child, which is the bottom row furthest to the right. That tree on the right-hand side is not complete because there is a gap at 6's right child. If that 7 instead was pointing to 6's right child, this would be a complete tree. But it's not. We kind of like skipped that little right child of 6. That's a gap. This is not a complete tree. Any questions? Yes? If you remove 7, is it complete? What do we think? Yeah, I agree. It would be. 7's really the one mucking it up here. Great. So it is a binary tree. Every node has at most 2 children. It has a heap ordering. Every node is smaller than or equal to its children. And it has a heap structure. Every level is complete, meaning no gaps. We are filling from left to right. Those are your requirements, your definitions for a heap. Is that a valid heap? Yeah, I agree. 8 is smaller than both 9 and 10. It is complete. Is this complete? Yes. Also, this one, if this helps your brain, this is kind of how I think about it. Like, this is how you would like store sequential numbers in a heap. This is totally valid. Is this a valid heap? No. Where have we got a gap? 2? 2's got a gap? There's another gap too. Where'd another gap be? 4, agreed. Yes. Gaps, no good. Does it maintain the heap ordering property though? Is every node smaller than its children? Yeah, cool. Great. Oh, thanks, Pass Casey. Yeah, great. Great, okay. Perfect. Okay, try it yourself. Go ahead, chat. Are these invalid heaps? Take a couple minutes. Oh, Lordy. All right, let's talk about it. I heard some really good conversations. Let's start with the tree furthest to the left. And we'll just go invariant by invariant. Does the tree to the furthest left, does it satisfy the binary tree requirement? Yes, yes. Every node has at most 2 children. Okay, does it satisfy the heap invariant? No. Does anyone want to tell me which nodes break the heap invariant? Anyone? Ooh, I heard some. Yeah, sure. 4, yes. So we've got 4 as the overall root. Is child 5? No problem. Is child 2? Problem. Are there any other nodes that break the heap ordering property that anyone can see? You don't see anymore? Yeah. 10 and 11. Let's see. Well, so 11 is greater than 7, and 10 is greater than 8. But if you look at the 2 and the 3, is 2 smaller? Oh, okay, great. I thought I mixed up 2 and 3. Sorry, I tricked myself. Don't look at your slides for too long, people. Okay, let's move to the middle tree. Is that a valid heap? Which properties does it satisfy? Does it satisfy the binary tree property? Yes, I agree. Does it satisfy the heap property? See, I also tricked myself on this one. Yes. Which node invalidates the heap property? I heard it. The 6 and the 7. The 6 and the 7 are not in the order we want them to be in. Because 6 is smaller than 7, it can't be its child. Does this satisfy the structure invariant? No. This is unfortunately that notorious degenerate. This is not a valid heap. Yeah? Okay, finally, tree on the furthest right. Does it satisfy the binary tree property? Does it satisfy the heap ordering property? Okay. Does it satisfy the complete property? Yay, okay, great. Oh, okay, thanks. Yes. Ah, invalid. Okay. These are my old-fashioned style slides. It's funny. Yeah. Any questions about these? Okay. So, because of the completeness, we do have a guaranteed runtime again of logarithmic runtime because we've got this nice sort of balanced tree. We're filling things up. So you can consider the height of any heap to be guaranteed to be locked at theta of log n. That means the time it takes to traverse from the overall root down to the bottom is log n. Great. Okay. How much time we got? Oh my gosh, we totally have time to do this. Great. So that's how a tree, that's just a tree existing in nature. That's just things that are true about a tree, a heap. Let's talk about how we actually implement the priority queue ADT using this magical data structure we've just learned about. Okay. Peak min. Here is a valid heap. How do we think we are going to implement peak min? Yes. Absolutely. There it is. I found it. I peaked. So peak min runs in constant time. Isn't that great? Because that is a really useful thing. Okay. Now let's talk about removeMin. This one I do not expect you to intuitively get at. So here is the thing. With AVLs and red-black trees, we sort of knew that the binary search property was the harder one to maintain. So we maintained binary search and then fixed the structure. Heaps are the inverse. We are going to maintain the structure, and then we will fix the ordering. So when we remove min, it means we are going to pull out that overall root. But that leaves us with a gap. Now, you would maybe be inclined to want to move the 4 or the 7 up, but the thing is the 4 and the 7 have their own children, guaranteed, as long as it's like a, bigger than 3 items tree. And so if I move 4 or 7 up, then I'd have to figure out what to do with their children, and so on and so forth. So instead, I am just going to replace that overall root with a node from the very bottom who I know has no children. So it's a really nice, easy one to pick up and drop in there because I don't have to mess around with the rest of the heap. But we have obviously broken the heap ordering property. So structure is retained, but the heap invariant is broken. So welcome to what we do whenever we have a broken heap. We are going to do these magical things called percolations. Okay, we are going to take a very short detour away from a requirement I know you've been living with, where we say never morph a node. That means once you make a node with a value in it, you never change the value. You only move the connections around. Like you've probably encountered that with linked lists. We're like, you can't just change the data field. You got to move it around. Forget that for the next 10 minutes and then the first 5 minutes of lecture maybe on Wednesday. What we are going to do is we are going to morph nodes, and we are going to do this thing where we just percolate the data values down within the nodes. So what we're going to do is we're going to say, well, now 13 is my overall root. Swap 13 with my smaller child. In this case, that's the 4. Great. Now I'm going to ask myself, do I still break the heap invariant? Yes. So I'm going to do another percolate. And so I'm going to swap with the smaller child. Great. Do I still break the heap invariant? Yes. So I'm going to swap with the smaller child. And now I have restored the heap invariant while maintaining the structure invariant. And all I've done is just sort of swap data fields. Questions? Yeah. Yes, we are just swapping the data fields. Here's my foreshadowing for Wednesday. It's because it turns out it is almost astronomically easier to implement this not with real nodes, but with an array underneath. So what you're actually going to do is just be swapping values in an array. But we'll get to that on Wednesday. I know. But you have to think of it in terms of a tree. But what's great here is When we think about the worst case runtime, we know we've got to, 1, we've got to find the last element in the list. 2, we know we've got to move it to the very top spot. And then 3, we got to swap until we get down. So in the tree version, finding where the last possible node is, that could kind of be like a linear runtime, unfortunately. But like I said on Wednesday, I'm going to show you something tricky, and I'll show you that will be a constant operation in the actual way we're going to implement the heap. Moving it to the top spot, that's like a constant. Just swap those data fields. And then the percolations at most are going to go through the height of the tree. So they percolate, even if it does just like this is kind of the worst case scenario where it has to percolate all the way back down. That is at most going to take log n runtime. Great. Yes, thank you. Yes, height of the tree, it dictates how long these things take. That's why completeness really helps us keep, we like a dense tree because that keeps the tree short. Okay, great. Why don't you guys practice? We do have time. Go ahead and perform a removeMin on this tree. What is the final result of that going to be? We're going to talk about it in 2 minutes. Go ahead. All right, purely in the interest of time, because I know it is a sunny day and you all want to get out of here at exactly 4:20. Does anybody want to walk us through what's going to happen? Can anyone tell me who is going to replace the 5? The 5 will be removed. Who replaces the 5? Anyone? Yeah, over here. 18, absolutely. That is the bottom level, rightmost. So we swap over 18. Great. Now, we do our percolations. Do we need to do a percolation? Who are we going to swap 18 with? 9. I agree. Do we need to do another percolation? Who are we going to swap 18 with? 11. I love it. Do we need to do a percolation? Oh! Structure maintained. Heap maintained. Congratulations. There we go. That is percolate down. Here's more examples. I'm going to end lecture there. Come back on Wednesday where I'm going to show you how to actually implement this without any trees. Yeah.